You flip a light switch, and your room lights up in an instant. Electricity must be one of the fastest things in the universe, right? Well, here's the thing. The electrons flowing through the wires in your wall are slower than a garden snail. Seriously. A snail cruises at about 1 centimeter per second. The electrons in your wires? They crawl at about 0.02 of a centimeter per second. That is 50 times slower than a snail. So if electricity is that slow, how does your light turn on so fast? To understand electricity, we need to start with something tiny. Atoms. Everything around you, your desk, the air, even your own body is made of atoms. And every atom has a core packed with protons, which carry a positive charge. Buzzing around that core are electrons carrying a negative charge. Charge is just a property of matter, like mass or color. Positive and negative charges attract each other like magnets. And when you force electrons to move through a material, you get something incredible. You get electric current. Now picture a copper wire, the kind inside every cable in your house. It is absolutely packed with free electrons, billions upon billions of them, just bouncing around randomly. When you connect a battery or flip a switch, those electrons start drifting in one direction. But they don't sprint. They barely crawl. In a typical household wire carrying about 10 amps of current, electrons drift at roughly 0.02 centimeters per second. At that speed, it would take an electron over 9 hours to travel just 1 meter of wire. Wait, 9 hours? But when you flip your light switch, the light turns on instantly. Not in 9 hours, not in 9 minutes, not even in a second. It happens in a tiny fraction of a second. Something does not add up here. If the electrons are barely moving, what is actually making your light bulb glow? This is one of the biggest misconceptions about electricity. Most people think electrons race through wires like water through a fire hose, but the truth is way more interesting than that. Think of it like a garden hose that is already full of water. When you turn on the faucet, water immediately comes out the other end, but it is not the same water you just pushed in. The water that was already sitting in the hose gets pushed forward by the new water behind it. The whole column of water moves at once. Wires work the same way. They are already stuffed with electrons. When a battery creates a push, it does not send its own electrons racing to your light bulb. It nudges the electrons that are already there. But here is the really wild part. It is not even the electrons themselves that carry the energy. When you flip that switch, an electric field ripples through the wire at nearly the speed of light. That is about 300 million meters per second. The field is like a wave in a stadium. Each person barely moves from their seat, but the wave travels across the entire arena in seconds. The electric field pushes each electron, which pushes the next one, which pushes the next. The signal races ahead while the electrons themselves barely budge. So what creates this push? That is where voltage comes in. Voltage is electrical pressure. Think of a battery like a tiny pump. One end has a bunch of extra electrons crammed together, and the other end is missing electrons. That difference in charge creates pressure, just like water pressure in a pipe. The bigger the voltage, the harder the push, and the more current flows. That is why a tiny AAA battery can power a remote control, but it takes thousands of volts from a power plant to light up your whole neighborhood. But not everything lets electrons flow easily. This is called resistance. Some materials, like copper and silver, let electrons glide through with barely any friction. We call those conductors. Other materials, like rubber and glass, hold on to their electrons so tightly that almost nothing gets through. Those are insulators. That is why electrical wires have a copper core wrapped in rubber. The copper carries the current, and the rubber keeps it from escaping into your hand. And the reason wires heat up? That is resistance at work. Electrons bumping into atoms, turning electrical energy into heat. Now here is something that will really twist your brain. The electricity in your house is not even moving in one direction. It is alternating current, or AC. That means the electrons in your wall are constantly switching direction, back and forth, 60 times every single second. They are literally just wiggling in place. They never actually go anywhere. Imagine a crowd of people swaying left and right, but never taking a step forward. That is what the electrons in your house are doing right now. They are dancing in place, and somehow your lights still turn on. So if the electrons are barely moving and sometimes not going anywhere at all, where does the energy actually come from? Here is the mind-blowing answer. The energy does not travel inside the wire. It travels through the invisible electromagnetic field surrounding the wire. The wire is just a guide, like a train track. The train track does not carry passengers by itself. It just tells the train where to go. The electromagnetic fields around the wire carry the actual energy from the power plant to your light bulb. The wire just shows them the path. And then there is lightning, nature's most extreme display of electricity. When charge builds up in storm clouds, trillions of electrons break free all at once, ripping through the air in a massive bolt. Lightning heats the air around it to 54,000 degrees Fahrenheit. That is 5 times hotter than the surface of the sun. For a split second, the air itself becomes a conductor, and electrons blast through it with violent, beautiful power. A single bolt can carry up to 1 billion volts. That is 10 million times more than the outlet in your wall. So the next time you flip a light switch, remember what is really happening. The electrons in your wire barely moved. They are slower than a snail, slower than almost anything you can imagine. But an invisible wave of energy, carried by electromagnetic fields, shot through the space around those wires at nearly the speed of light. Electricity is not what you think it is. It is not fast electrons sprinting through copper. It is slow electrons being gently nudged while invisible fields do all the heavy lifting. And honestly, that is way cooler than anything you learned in school. If you like this video, check out one of these, and don't forget to subscribe.